We continue with our discussion on speed control of shunt and separately excited DC motors. In last class, we discussed about this. We started the discussion about speed control of shunt DC motors. We discussed that we can control the speed of shunt DC motors or separately excited DC motors by three methods. First one was by adjusting the field resistance RF, which in effect actually means changing the flux. The second method was adjusting the terminal voltage VT. And the third method was inserting a resistor in series with the armature. That is changing armature resistance RA. The first method, that was adjusting the field resistance RF, basically, in this method what we basically change when we change RF, by changing RF, that is by changing the field resistance. If I have this figure here, by changing this field resistance, what I basically intend to change for fixed voltage, I intend to change IF. That is, we intend to change IF, field current. By changing field current, we basically intend to change flux. Thus, this method is also known as speed control by changing the flux. When we increase RF, that is when we increase the resistance, let us suppose we increase the armature resistance. We increase the field resistance. When we increase the field resistance, we are decreasing the field current. If we decrease the field current, we are decreasing the field flux. Also, we know that induced EMF in the armature is proportional to K, Phi and Omega. Suppose speed is constant for time being. If you are decreasing flux, so since K and Omega are constant, so flux Phi is decreased. When flux Phi is decreasing, so EA, induced EMF, is decreasing. When EA decreases, from this expression IA equal to VT minus EA by RA, since EA is decreasing, so this expression is increasing, or EA is increasing, so IA is increasing, so armature current is increasing. When armature current increases, we know torque induced is K Phi IA. This K Phi IA increases because IA increases. Here you may ask that, sir, since induced torque is proportional to K, Phi as well as IA, since we are decreasing flux Phi A and current IA is increasing, which way will induced torque go? Will induced torque decrease because flux is decreasing, or will induced torque increase because current is increasing? We'll say this in numericals, that for a percentage, for 1% change in flux, the percentage change in current is much more. I'll repeat this. For 1% change in flux, percentage change in current is much more. It's around 50% for a typical motor. That means if in a typical motor you are decreasing flux by 1%, this current will increase by 50%. So overall effect on induced torque is that of the current. That is, induced torque will increase. Current will have much more predominant effect than the flux. When induced torque is increasing, since load torque is constant, that means induced torque is more than the load torque now. When induced torque is more, load torque on the motor is less, so this motor will start accelerating. That means its speed will start increasing. When its speed starts increasing, that's omega is increasing. Now, what happens to EA equal to K Phi omega? That is induced EMF. This induced EMF will start to increase now. When induced EMF will start to increase, this VT minus A will start to decrease. When IA will start to decrease, that means tau induced will start to decrease. When tau induced will start to decrease, then tau induced will again become equal to tau load, but at a higher speed. That means again this motor is in steady state condition. Induced torque is equal to load torque. But now this happens at a higher speed. Thus, we have increased the speed of this motor. If we want to decrease the speed of this motor, we have to decrease this RF. When you decrease this RF, when you decrease field resistance, current will increase, flux will increase, and the things will repeat itself till speed is lower. Motor is running at a lower speed. Fine? Okay. This was the method of by change speed control by changing the flux. Now second method is speed control by changing the armature voltage. Speed control by changing the armature voltage. Let us suppose this is the field circuit. This is R adjustable, this is RF, this is LF, this is VF. On this side, armature resistance, this is EA, RA, and this is variable voltage VT. This voltage is variable there. This is what you call as by changing the armature voltage. Let us suppose if I decrease this terminal voltage, I am not changing the field circuit at all. That means field voltage is constant, field resistance is constant, so field current IF is constant, so field flux is constant. Fine. We are not changing anything with the field circuit now. Now in this case, let us suppose I am decreasing this terminal voltage VT. Since we know expression for this motor VT for armature circuit is equivalent to EA plus IA RA. Or we can also write this as IA is equivalent to VT minus EA divided by RA. Now what we are doing here is step 1. We are decreasing VT. I'm decreasing terminal voltage VT. Now let's check what happens here. As we decrease VT, you are decreasing VT over here, IA will decrease definitely. Current IA is decreasing. Now, we know induced torque is equivalent to K phi IA. I have not changed, K is constant, I have not changed flux. Current IA is decreasing. When current IA decreases, what happens to induced torque? It decreases. When induced torque decreases, load torque is same, tau induced is less than tau load. Now load torque is same, induced torque is decreasing, so induced torque is less than load torque. What that implies? Deceleration, or omega will decrease, speed will decrease, because induced torque is less, load is more, induced torque is less, so speed will decrease, motor will decelerate, omega decreases. When omega decreases, what happens to EA is equivalent to K phi omega. Omega decreases, EA will decrease. When EA decreases, what happens to this? IA is equal to VT minus EA by RA. Since EA is decreasing, this term is decreasing, overall this will increase. When this will increase, IA will increase. Increases. When IA increases, that implies tau induced is equal to K phi IA increases. When induced torque tau increases, such that when implies that tau induced again becomes equal to tau load, but at lower speed. That means we have reduced the speed of this motor. Fine. Now, what are the applications of these two speed control? Where do we use these two speed control methods? Changing the flux or changing the field resistance and changing the armature voltage. If you could observe here, the field resistance method, when I increase the field resistance, current decreases. That means more the field resistance, less the current, higher the speed. So if I want to increase speed, I have to decrease the current by increasing the field resistance. That's not an issue. I will increase field resistance, current will decrease, so speed becomes higher. But if I want to reduce the speed, if I do not want to increase the speed, I want to reduce the speed using the field resistance method, I will have to decrease the resistance. When I will decrease the resistance, current has to be increased to produce more flux. In order to decrease the speed, I have to increase the field current. But how long can I increase this field current? Can I increase this field current indefinitely? No. Since there's a limit to the field current in the field circuit, you cannot increase current beyond the rating of the field circuit. That means there is an upper value, there is an upper limit to this field current IF. You cannot increase the field current IF beyond a certain point. When there is an upper limit, on the field current, so that means there is a lower limit on the speed control achieved by field resistance method. Because increasing the field current would have reduced the speed. When I cannot increase the field current above a certain point, that means I cannot decrease the speed by this method below a certain point. So what we finally concluded here, that is field, I will call this field current versus armature voltage method. In field current, IF is to be limited below the rated value. You cannot increase field current beyond the rating. There's a rated value of field current. In field circuit, there's a rated value of current. You have to limit the current up to the rated value. That means there's an upper limit on this field current. When there is upper limit on the field current, that means there's a lower limit on the speed. Thus, there is the lower limit on the speed control achieved by, thus there is the lower limit on the speed control achieved by field current control, or we can directly call this RF method. So by this method, by field current method, you cannot reduce the speed below a certain value, because reducing the speed below a certain value means increasing the current above the rating, which is not possible, which will damage the motor. But for increasing the speeds, if you want to increase the speed above the rated speed, for increasing the speed, current has to be decreased. For higher speeds, if you want to obtain the speed more than the rated speed, you will have to decrease the field current. Does decreasing the field current have any problem? No, you can in fact reduce current near to the zero value. You can reduce current continuously up to the zero value. So you can have very small value of field current, and you will have at that time very large value of speed. You will have a very higher speed in the motor. That means though this method, field resistance method or field current method, cannot be used to produce very small speeds in the motor. This method cannot be used to obtain a very smaller speeds in the motor. But this method can be effectively used to produce higher speeds in the motor. So this is point number 1. And what is the argument and what is the statement that we will make about the armature voltage method? Let's have a look here. In order to decrease the speed, if you want to reduce the speed, as we just checked over here, if you want to decrease the speed, you will reduce the terminal voltage. If you reduce the terminal voltage, you will decrease Vt, that will decrease Ia, that will decrease tau induced, that will decrease speed, and finally motor again comes to steady state but at lower speeds. That means to decrease the speed of the motor, you will have to decrease the terminal voltage Vt. But if you want to increase the speed, of motor by using the same armature voltage method, to increase the speed, you will have to increase this terminal voltage Vt. Increasing terminal voltage Vt will then increase the armature current Ia. But can I increase this terminal voltage beyond the rated voltage? there is an upper limit on this voltage Vt equal to rated voltage. Can I increase this voltage Vt above the rated value? No, I cannot. That will damage the motor. So this Vt is to be limited below the rated value. Vt has to be limited below the rated value. That means you cannot increase this Vt above the rated value. When you cannot increase this Vt above the rated value, that means you cannot increase the speed above a particular speed. Thus, there is the upper limit on the speed control achieved by armature voltage control method. I will repeat this once more. If you want to increase the speed, you will have to increase the terminal voltage. If you want to decrease the speed, you will have to decrease the terminal voltage over here. This is simple here, as we discussed in this. Now, if you want to reduce the speed, you will have to reduce the terminal voltage. There is no problem in that. You can reduce this terminal voltage. In fact, you can asymptotically reduce this to zero voltage, zero value. Decreasing the terminal voltage is not an issue. When you can decrease this continuously till zero value, you can reduce speed continuously from rated value to zero value. You can reduce the speeds below rated value. But if you want this motor to run above the rated speed, you will have to increase this Vt above the rated voltage, but which you cannot do, because if you increase this voltage above the rated value, that will damage the motor. So there is an upper limit on this Vt. When there is an upper limit on this Vt, there is an upper limit on the voltage, upper limit on the speed control achieved by armature voltage control method. Thus, for speeds below the rated speed, we use armature voltage method. And for speeds above the rated speed, we use field current method. Because if you want speed less than the rated value, you can reduce the terminal voltage over here. If you reduce the terminal voltage over here, speed will decrease and there is not an issue in the motor. If you want speed above the rated speed, if you want speeds above the rated speed, you can reduce field current over here. If you reduce field current over here, speed will increase, but reducing the field current is not an issue. You can easily reduce this. Thus, for speeds below the rated value, we use armature voltage control method, and for speeds above the rated speed, we use field current method. So this is used below the rated speeds, and this is used for above the rated speeds. Thus, in a shunt motor or in a separately excited motor, if we use both the speed control methods, we use field control methods above the rated speed, and we use armature voltage control method for below the rated speeds. You can have speed control in a motor as high as 40:1. You can have speed controls as high as speed control ratio as high as 40:1. What is the speed control ratio? That is highest speed to lowest speed. This shows the range. You can have the lowest to the highest ratio, lowest voltage to highest voltage ratio. 1 is to 100. That is, if smallest voltage is 1 rpm, highest voltage is 40 rpm. If smallest voltage is 10 rpm, highest voltage is 400 rpm. If smallest voltage is 100 rpm, highest is 4000 rpm. Look at the speed control available if you can use both the methods together. Fine. This is how basically it is done in a real DC motor. Now we'll very quickly have a look at the third method, what is known as armature resistance method. In the last class, we discussed that this method is seldom used in real practical applications for speed control. Why? Because using this method, you are inserting a resistance in the armature circuit. Since whole of the current will pass through this resistance in the armature circuit, if I had a figure over here, what we mean to do is you are inserting an additional resistance here in series with the armature. This IA current, whole of this IA current will pass through that resistance that you have inserted in the armature circuit and will produce losses, that is I square R losses, IA square RA, where RA is the value of resistance inserted in the circuit. It will produce losses in the circuit. So this is a wasteful method. You are basically wasting the energy over here in the armature circuit, in the resistance. There will be heating of the resistor. For the sake of argument, how this method works basically, in last lecture we discussed omega is equal to Vt by k phi minus Ra divided by k phi square into tau induced. You can refer to last lecture. And please go through lectures sequentially. First look at lecture 1, then watch lecture 2, then watch lecture 3, 4, 5, 6 and so on. Don't just jump into on lectures, lecture 4 first, then lecture 1, then 3, then 5. No. By armature resistance method, what we can basically achieve here is Ra is present here in the slope. That means if this is tau induced and this is omega, we discussed this is the curve of terminal characteristic of a shunt DC motor, omega versus tau induced, where the slope is given by Ra by k phi square. From this expression we can directly tell if we increase the value of Ra, what happens to this slope? The slope increases, so this will be more steeper. Increase this further, this will be more steeper. Let's call this as R1, let's call this as R2, this is R3. That means slope corresponds to resistance R1, R2 and R3. Armature resistance, of course. Which one is steeper? R3 is steeper. So which is the largest value among the three? R3, because slope is equal to Ra by k phi square. This has the steepest slope, so this resistance has to be more than this and this has to be more than this. So R3, I've write it here, R3 is greater than R2 is greater than R1. Fine. Now you can directly look here. Let us suppose this is the value of load torque, T load. And for motor to operate in steady state, this T load should be equal to T induced. Then induced torque is also equal to this value. Since load torque is this much, induced torque is also this much. If you have this much resistance, if you have this much resistance, if you have this much resistance, if you have RA corresponding to R3, let's call this RA3, RA2, RA1, RA3, RA2, RA1. That is our armature resistances. You will have this value here, you will have this value here, you will have this value here. This is speed corresponding to resistance Ra3. This is speed corresponding to resistance Ra2. This is speed corresponding to resistance Ra1. I will call this speed as omega 3. I will call this as omega 2. I will call this as omega 1. Corresponding to 1, corresponding to 2, corresponding to 3. Since load is same in all the three cases, T load induced torque has to be equal to the load torque. Since Ra3 is greater than Ra2 is greater than Ra3, but omega 3 is less than omega 2 is less than omega 1. So omega 1 is greater than omega 2 is greater than omega 3. That is by inserting the resistance in the armature circuit. By inserting the resistance in the armature circuit, the higher the resistance, the lower the speed. Fine. Thus you can control the speed of shunt DC motor and separately excited DC motor by inserting the additional resistance in the armature circuit, and higher the resistance, lower will be the speed. Lower the speed resistance, higher will be the speed. But this method is not used in practice because this is a wasteful method. You are basically using, since the since when you insert the resistance in series with the armature, whole of the current flows through that resistance and produces the I square R losses, which is basically the waste of energy. So this method is not used in real practice. Fine. But for laboratory demonstrations, you can check it in the laboratory. Okay, we finish this lecture and we'll start permanent DC motor next class.